So my name's David Burrell. I work on Oculus SDK team. I'm responsible for engine integrations. We have actually a bunch of people working on that with Unity and other engines. So we worked closely with Unity to get first-party support in. So that's that new checkbox that you've heard about. And before that, we were also maintaining the plugin, and then we have other work with them that should make the dev process easier, help you get better performance and functionality. So I just want to say right now, if we run out of time and you don't have a chance to ask your question, we're always available. So go to forums.oculus.com. You can always reach out. But this is a developer talk, so it'll be somewhat technical. We're going to be talking about optimizing performance of your application. This is kind of a relevant problem because as we get closer to the CV1 launch, I'm not supposed to say that, the Rift launch, performance constraints are going to be tighter because you're rendering so many pixels, and there's also a lot of performance constraints on Gear VR. So one common issue that people have is dropped frames and overrunning their performance budgets. So the goal here is to help you with that. But I'll motivate it a little bit with some VR theory. So first of all, if you're new to VR and Unity, Pete Moss demoed it yesterday, and it was actually pretty simple. You just go into the build settings and click, or player settings and click virtual reality supported. And if the user, by default, that'll use the Oculus VR device currently. But as other VR devices come in, there may be a way of selecting the default one here. But the current behavior is that if you have this box selected, it then includes VR support in the built player. And when the user tries to run the player, it'll initialize to VR mode if a VR device is connected and working properly. If any of those conditions is not met, or if you uncheck the virtual reality supported box, then the app will just start up with normal monoscopic rendering. So if you're developing your app for VR, you should at least have some thought put towards how it's going to behave in mono, because it may fall back to that in a failure mode. If you do not check the virtual reality supported box, there's actually content that leaves out of the standalone player, so you will not be able to enable it later. So if you're not designing for VR, leave this unchecked, and there's no risk of someone turning it on when you ship. Okay, I should also contrast this with what we were doing previously. So in Unity 4, we had a plugin architecture that was built on top of Unity's rendering plugin system, and it was a lot more invasive in terms of how Unity performs rendering. And there were also a lot fewer use cases we could support. So things like linear lighting and sRGB should work better now after we fixed a bug recently. But that's kind of how most Unity 4 apps still work. So if you are using Unity 4, we do still support that, although it's kind of on live support, and we prefer that you upgrade to Unity 5 as soon as possible. There are also performance advantages to doing so. Okay, so once you import we still have a package that's not necessary. But it's a set of utilities that help you develop VR more easily. So we provide things like a camera rig that gives you anchors that follow the tracking. There is already a script API built into Unity, and you can easily implement the same thing yourself. But we just kind of give you some reference prefabs and a player controller that's optimized for comfort and a couple of other things. So if you download the Oculus utilities, it'll help get started. The camera reference frame. So if you're using our OVR camera rig, who here has built an app for the Oculus Rift? Oh, a lot of you, okay. And how many of you were using the Unity 4 integration? Okay, a lot of you, yeah. So the OVR camera rig is a prefab that we had back then, and it still works with the utilities, although it's optional now. You can just take a plain camera. And in both cases, the initial pose of the camera is kind of the origin of the frame of the tracking reference frame. And then we call that the initial center eye pose, and tracking is applied relative to that. But you can prevent that and have like an absolute frame of reference that's based on our tracking reference frame, or based on our actual tracking data, by unchecking use profile data. I guess it's only available in the C# API. Excuse me. Okay, so a little background on VR that'll help us through the rest of the presentation. In case you're not familiar, VR involves rendering to two eyes, rendering separate images, and then also updating what you render based on the user's motion. So in the simplest case, we have Gear VR, or DK1 if you've ever worked with that, where we use nothing but an inertial measurement unit, which is a combination of an accelerometer and a gyroscope. So there's actually a small ASIC on the chip or on the plastic headset that you connect to. That's a slightly higher precision inertial measurement unit than what you'd find inside the phone. But over time, you may see phones incorporate IMUs like this. So this will provide most reliably a rotation, and then we infer a position based on that. Unfortunately, the raw position data that you would get from an IMU these days tends to drift a little too quickly for us to use directly. But we can assume that your head is a ball on a stick, and if you're mostly stationary, then as you look around, it should translate as expected. Another thing that our SDK does is try to correct for latency. So once we've got your head pose, we feed that to Unity, and it renders the two eyes from slightly different poses based on the eye offsets. And then it provides us both of those images in textures. We apply a bunch of post-processing to those textures, including lens distortion, chromatic de-aberration only on PC, because on mobile it costs too much texture bandwidth. Although you can enable it if you're going for all-out fidelity. And we also perform this latency correction that we call time warp. So the idea here is that as your head moves and we render a frame, any point in time in which we sample your head pose, we start rendering then, and then by the time we're done, 10 milliseconds or so has elapsed. And so there's a significant amount of error in that initial pose. So whether we predict it or whatever we've done, it's likely to be more correct if we resample after rendering. And so that's exactly what we do here. And fortunately, most of the error in the image resulting from the head pose change is due to the rotation change of your head, because the translation results in relatively little what we call optical flow, which is something we'll get into in a moment here. So since we can assume in many cases that the rotation is the most significant source of error, we can just correct the rotation of the image by performing a panoramic shift of the image. So what we're showing here is a very significant time warp shift, much more significant than we apply on a per frame basis. But just to illustrate the concept, the user has looked at the house, it started to render, then they moved their head up here by the time it was shown to them. So we shifted the image down to where it should be. So on PC, we perform a correction like this every single frame, and it's executing in lockstep with your code. This provides very low latency and very predictable time rendering times, frame times, between the time the IMU is sampled and the time you see the image. I should point out that on PC, we also use computer vision to track the position of your head, in addition to the rotation provided by the IMU. They work in concert with sensor fusion to provide kind of a high-frequency reading that's also giving you an accurate position. Anyway, that's beside the point. So with synchronous warp, they execute in lockstep. And if you ever fail to render within the 10 milliseconds or so that you have, you'll miss that frame, and the image from the previous frame will remain on the screen until another 10 milliseconds later, which can be very jarring for the user right away. It's a little bit different on mobile, where we have what we call asynchronous time warp. And the difference there is that we warp at a constant rate, regardless of whether you're rendering at a constant rate. And so we're able to preempt your rendering with our distortion rendering due to some collaboration with Samsung and their drivers. By the way, asynchronous time warp is likely to show up on PC at some point. The idea here, though, is not to allow you to render at 30 or 20 hertz. That will still cause significant artifacts. The idea is that it's kind of frame rate insurance, so that if you do, you're right on the border most of the time and you drop a few frames here and there, those won't cause jarring artifacts for the user. So in any case, you do need to spend considerable time optimizing your program. So to give you a little more detail, the consumer Rift is going to have 90 hertz refresh rate and roughly 3 times the pixel fill of a 1080p render target at 60 hertz. So that's significantly more pixel throughput than you may be used to rendering. And a lot of people are complaining about the short time they have to do this rendering. Unfortunately, that probably does have implications for the quality of your graphics. You're going to need to try to optimize that as much as you can. We also do try to help you with a recommended spec, so your users should not be running GPUs lower than a 970. But of course, we all try to do that. I run VR all the time on my MacBook and get horrible frame rates. So, the problem is we need to set expectations here. Realistically, you're not going to get good VR out of like a 750M. And then on mobile, the constraints are even tighter. But fortunately, you only have to render at 60 hertz, and we're only rendering at 1024 squared render target. So that's about the same pixel fill you might have had before. It's a little bit higher, but the problem there is that you can't have very much variability in your rendering times. And there's actually a little bit less pipelining available on the PC due to the lack of what we call queue ahead. So this is an important contributor to latency. Many engines try to optimize for throughput, and they'll queue several frames ahead, or at least one frame ahead, and try to overlap one frame's CPU work with the previous frame's GPU work. Unfortunately, that can lead to well over 20 milliseconds of latency, and we try to limit the queue ahead to no more than a quarter of a frame, which is still generally enough to kick off a lot of the work you need. It's kind of a compromise in a gray area, unfortunately. So, given all of that, what's the matter with dropping frames? And what's the matter with latency? Well, the problem is that you have all of these systems in your brain that compare different signals that you're getting. And unlike other game technologies in the past, well, and like some, if you don't get those signals consistent with each other, your user is going to feel discomfort, and actual, tangible discomfort that makes them want to rip the headset off of their head. And we've probably all experienced this, so it's no surprise. But there's a lot that you can do to avoid the issues. Unfortunately, discomfort is not really ever worth more graphical quality. So if you were to try to render advanced parallax shaders or volume rendering that cannot possibly complete within 10 milliseconds, it's almost never going to be worth the low frame rate that would incur. So the first pair of signals that we can talk about is the vestibulo-ocular reflex. The problem is that your eye, well, it's not a problem. Your eyes and your ears both sense your acceleration. You have this concept of vection in the stuff that you look at. So in this illustration here, there are features, kind of high-frequency details in the image that your brain latches onto, and as you move towards them, it notices them moving outward from a certain point, and then it can tell that you're moving towards a particular point at a certain speed. It compares that signal to another sense in your inner ear, called the vestibular sense, that detects pressure on these bags of fluid, basically. It's like the motion of this hair, I think, actually. But the point is that if those two signals don't agree, your brain starts to send up a red flag and says, oh, my whole frame of reference is wrong here. Something has to give. And we're not really sure why, but that makes you feel nauseous. There are a lot of evolutionary theories on why that would be. I don't want to speculate, but it does make you feel sick. Different people have different levels of susceptibility to this. And VR developers are often the worst testers for this because we've got our VR legs. Although I don't really believe that VR legs is a thing. I think we just develop a tolerance to the pain. So we're definitely not the people who should be saying whether or not a particular technique is going to make people sick. We usually, at Oculus, we use what we call a simulator sickness questionnaire, which we give to people, and then we perform a technique or have them look at a certain scene, and then we'll give it to them again and see the difference. And then you have to do it in a statistically valid way. It's actually kind of difficult. But we've noticed patterns in different types of stimuli that cause simulator sickness. And it's definitely the case that higher latency contributes to it. So just reinforcing the concept of what a drop frame does to your latency, here you can see that sawtooth signal of the latency increasing over time as I deviate from the point at which I sampled the IMU. If I drop a frame, then suddenly I'm at possibly 30 or 40 milliseconds of latency, which is going to start to be uncomfortable for people. So what can you do about this? Before you ever do any profiling, you can eliminate draw calls, you can eliminate triangles, you can try to reduce the complexity of your shaders. Remember, on Gear VR, there are very tight constraints, and you probably always want to keep an eye on Unity's stats view. Although it does tend to somewhat inflate the stats, it gives you a ballpark. And the actual number of draw calls that you're issuing should be no more than 100,000. Now, these are kind of soft numbers, and if you do exceed them, you can probably save the performance in another part of the app. So don't take this as like, set in stone. Do experimentation yourself, but this is kind of the budget, the envelope that we've found. Oh yeah, and another point is that if you have optimized and you're hitting frame rate and you're not concerned about the latency, there's still good reason to continue optimizing on Android because the device does get hot and it consumes a lot of battery. So if you optimize it down to 0, it'll never run out of power. It'll never get too hot. The device will be less prone to fogging up. So that further increases comfort. Another thing that you're tight on is texture throughput, or texture bandwidth. So you want to compress your textures as much as possible. I would recommend using ASTC and GLES3 within Unity. The GLES2 stack still kind of works, but if you're using ASTC or ETC2, you can run into problems there. So the most robust path I've found is GLES3 plus ASTC. Also limit the resolution of your textures. Throwing giant textures in there is only going to cost you a lot of lookups and sampling and interpolation. So just try using the lowest MIP level or the lowest MIP detail that you can, and just have your artists look at a particular iBuffer resolution as they're tuning things. Also bake as much of your lighting as possible because the pixel shader complexity will hurt a lot. So, in Rocket Toss, has anybody here played Rocket Toss on our mobile SDK? Great, that's one of the samples we ship. So it's a pretty rich visually app, and we only do actual specular lighting on the objects that are moving. Fortunately with Gear VR, since there's no positional tracking, you don't notice to that great of an extent if the specular highlights don't move. So on stationary objects, we actually baked those, which saved us a lot of perf. Another thing you can do is use the simplest meshes possible to reduce the polygon count. This is much more important on Android, and you're probably going to find generally about an order of magnitude more performance headroom on PC. So I generally have like a quality setting for Android and one for PC, and then a third one for really high-end PCs. But Unity lets you tune the distance at which it switches meshes. And if you're using billboards, be careful. If the billboard covers a lot of the screen, you probably don't want to have it set to turn and face the user. Not only does that look incongruous between the two eyes, which is very uncomfortable, it's one of those many signals that your brain compares. And if it sees, what it thinks is the same image in both eyes, but they're perturbed in some way other than just being projected differently, it also starts to send up red flags, and you start to feel maybe cross-eyed or just can't make sense of the image. So billboards are one of the things that can trigger that, but also different aliasing in the two different eyes if you're using extremely low resolutions. So those are things to avoid. You can choose imposters that are stationary in world space that are mostly projecting the same way to the two eyes. Try to have them far away from you, relatively low screen coverage. That gives good results. We have a sample we'll ship before too long that shows like an asteroid field that does this, and it's pretty effective. Another really great way to reduce both pixel fill and texture bandwidth is to reduce the buffer size for the eyes. So Unity exposes this as VR settings.renderscale. And the way that that's implemented, if you make that a larger number than 1, it'll reallocate the texture with that new size, a multiplier of what we recommend as the resolution to get 1 pixel per texel in the center of the screen. As you go out from the center, the pixel density, like the number of texels per pixel increases. So this is kind of the minimum pixel density, the minimum texel to pixel ratio. So we set that to 1 by default, which is actually a little bit aggressive, and it does burn a lot of texture bandwidth and fill rate. So if you don't notice a quality difference, dropping that to even just 0.8 or 0.7 will save you up to 50% of your pixel throughput. So here, I mean, you can't really see this because I've resampled, the PowerPoint presentation is doing all kinds of other effects to this image, but you really can't see a dramatic difference, even going down to 0.5. If you're looking at it through a Gear VR, it would be less significant of a degradation than looking through the Rift. Another thing you can do is try to vary this dynamically. I haven't found a great policy for doing this yet, but there are ways. I'm sure if you try to do it without risk of hysteresis, you could just try to look at what phase the program is currently in and just take an average over a minute or so, and just select a pixel density. Okay, so Unity offers the render scale, like I mentioned. It also allows you to turn off mirroring to the main display. That's the show device view. And then you can also have it render the same image to both eyes, which will make it look stereo incorrect, but if most of your content is very far away, that's pretty significant savings in render cost. You can also select between multiple VR devices if you have them plugged in there, and disable VR completely. Okay, so we're getting very low on time. I'll try to zoom through this, but if you're still not hitting frame rate after adjusting all of those levers, then there are tools that you can use to dig in. And in general, I would suggest starting out at a high level, don't optimize too early, and dig in and try to identify where your app is spending the most time and optimize that first. That's kind of a variation on Amdahl's law, where you optimize the thing that's going to have the highest ROI. So we offer you a really simple tool called the Perf HUD, which you can toggle at any time using our configuration utility for any app. And it'll just show you how much time the GPU is spending rendering the textures before we get them. It'll also tell you how long it's taking us to perform the distortion, but you generally have little influence over that. And the most interesting thing is the amount of GPU time that's being spent. If that's relatively low and you're still not hitting frame rate, then you probably are CPU bound and should look at the CPU profiler in Unity. Also, on PC, GPU profiling is possible through Unity's powerful profiler. If you're not hitting frame rate, then there are a couple of actions you can take. You could try taking subsets of your scene. Who here has had to hit frame rate right before ship and has had to experiment with a lot of different techniques? Okay, yeah, so it can be non-obvious, but oftentimes, you'll subdivide down and find, oh, there's some torus in a shoe that someone tessellated at an extremely high degree. And things like that are easy to shake out by just kind of taking subsets of your assets. But in some cases, there might be other issues you can't narrow down that way. And so in this case, you probably want to look at Unity's hierarchy view. In this case, I'm looking at the CPU, and it's waiting for the GPU to finish commands. You're going to see these purple bars here, but that's normal. It's just waiting for vsync, because when VR rendering is enabled, we always wait for the vsync to get predictable latency. That doesn't mean that so disabling vsync is not worth the performance gain that you do get. So most people coming from traditional game development are used to getting a 50% performance gain from turning off vsync, and unfortunately we really need to leave it on here. Oh, but there are spikes in this profile, and this is kind of interesting because the green spike there, it looks like there's something going on in the GPU that's taking much longer than it should. But then there's another purple spike later, and that's just a plain old CPU spike, so doesn't seem to be a sudden increase in utilization on the GPU. So why don't we drill down on that a little bit? Unity also has a timeline view. So that's over here. If you click on the hierarchy drop-down there above that highlighted blue Oculus Wait for GPU, you can also select timeline. This is an extremely useful view that I find very few people are aware of in Unity. It'll tell you what Unity is actually working on at each point in time during the frame, which was added in, I think, 5.1. Okay, so if that doesn't answer your questions, you can also use GPU view. So Windows has a very powerful built-in subsystem for tracing events that you can enable via the xperf tool. We try to wrap all that and make it simpler for you. So if you've got the runtime installed, you can go into the tools ETW directory and run our overlog.cmd file. That'll install our manifests for dumping events. And the overhead of this, again, is very minimal, but it'll give you just a ton of information about what the whole system is doing. So you run that, and then you run your app, and then you run the OVR log command again to turn it off, and then you can open up the resulting trace in a variety of tools. It dumps in a standard ETL file, which can be opened in Windows Performance Analyzer or GPU view. So here I'm talking about GPU view. We were looking at that issue a moment ago where there was a spike on the CPU. And here we can see at a high level, like, each frame is rendering, and there seems to be like a bit of a hiccup towards the middle there. So we can zoom in on that and look at this mountain of work that occurred in the middle of the frame. So in GPU view, you have, over time, these vertical stacks that appear each frame. What those stacks represent is the queue of work on each resource. So each of these horizontal lines is a queue, is a resource that's essentially serving what we call packets. And each vertical stack within there is, at a point in time, how many packets are queued waiting on that resource. So GPU view will tell you which packets are kind of interdependent. So if you were to click on one of these purple bars down here, it would also highlight one of the purple bars up on the GPU. So down here we have the CPU as a resource. And then on the top we have the GPU, hardware queue, as a resource. And GPU view is great for finding the queuing behavior in your system. So what on the CPU is forcing the GPU to wait and vice versa. So in this case, we actually had the GPU waiting on the CPU because there was a vertex buffer page fault. Well, it was actually kind of a pileup. So the GPU was waiting on the CPU, was waiting on the GPU. But as a result, 2 frames worth of work came in here and just piled up and didn't retire in time. So we ended up dropping a frame, resulting in that spike in the Unity profiler. So insights like this are really valuable. I would really recommend familiarizing yourself with GPU view. It has kind of informal but really good documentation. If you just dig in, just Google it. It comes with the Windows 8.1 SDK. And if you're on Android, unfortunately that's not one of the tools, but we have systrace. And there's also this other high-level tool that we wrote at Oculus called OVR Monitor, which you can attach to the app. It'll show you the render target, each frame, as well as all the EGL calls that were made and the VR API calls. So you can kind of get a sense of how long each frame is taking to render, what our SDK is doing, and whether the cores are being throttled. That's what the bottom blue bars represent. So I mentioned systrace. This is kind of what you would use for drilling in. Unfortunately, it has relatively little information about what the GPU is doing. So in a lot of cases, you end up reading a lot of your code and trying to make perturbations and see the impact. If you're working on Adreno with like Note 4 that uses Adreno, you can use the Adreno profiler, or you could use the Snapdragon profiler to get more insight on what the GPU is doing. There are other tools as well that can be useful. I would definitely recommend trying out a variety of them and see which ones work the best for you. And then we kind of already covered this, and I'm out of time. Any questions? Thank you.